But we had what we had your discussed Satish Pai there are 20 delegates can be. So basically, we will take delegate from CN all that. Good if we can make the 20 is as such we never give, but 20 we are making. And then individual they come there. No, not for that point. Whoever is there is the top bosses and what there are 20 people, the rest, particularly ABS and governments. And others are all going to take up their project. So please just see, as such you are guest, but we have made it 23 delegates, but so I'm going to meet 5th September to this class. I have to be informed of this. And I will also try to convince him that 20 you take from all the HODs and all those people who are chairmen and others. Okay. Just see. You are part of your. Yeah. So those 20 can, under 20 you can come. I think that will be no problem. As it. And sure. You are, yes. I will take care. We will take care. This thing that you are part. Okay. Oh.
நீதா ஏன் லாக் பண்ண மீட்டிங் எல்லாம் இவ்வளோ
Welcome, ladies and gentlemen, in the IBAAS lecture series. And today we are having a presentation by S. Sasikumar, who is having long experience of working in alumina refinery and aluminium smelter. And at present, he is working as uh, chief of head of the Mahan aluminium smelter of Hindalco Industry and utilizing aluminium passionate technology, and he's highly experienced in aluminium smelting technology. So this will be about 40 minutes presentation, recorded presentation. IGAS office will run this presentation, and the topic of his presentation is addressing Amperage creep in aluminium smelter, strategies and effective solutions. So you are all welcome in IVAS lecture series for August and September. You know, we have our big conference. So September there will be no lecture series, and October, November again we will start our lecture series. And people are welcome to participate and present paper in this lecture series. This is journal technical lecture series, and you are all welcome to make your presentation. If you wish, and please contact us and we will invite you for the presentation. So now I will request IBAS office, because it's already 4 o'clock in the evening, and I will request IBAS office to start running the presentation of Mr. S. Sasikumar. You are all welcome. Over to IBAS office. Priyanka.
Hi, good evening all. First of all, I'd like to thank Ashok and the IBAAS team for providing me the opportunity to speak in this forum. I'll be speaking on the amperage creeps in potline, what are the challenges which is being faced, and we will also discuss on the effective solutions which can be implemented to have a smoother and faster amperage creeps. So the overview of the presentation will be covering the industry background. We will also discuss on the amperage increase impacts and what are the challenges and systems while we do an amperage creep. And we will also have some conclusion at the end of the presentation. So seeing the global scenario, the primary aluminum industries has changed very largely in the last 25 years. So on a volume perspective, if you see that there was around 40 to 42 million tons in the year 2010, but right now the capacity has been around 71 million tons per annum. So the huge production increase which is happening in China. They have been at around 2 million tons per annum in 2000, and right now they are at 41 MTPA. In the rest of the world, the volume remains the same. The production in the Western world has come down because of the high energy cost. And in the GCC area, there is an increase in production. And of course, this area has developed their own technologies, which is being implemented in this Gulf region, as well as also outside. Going forward, sustainability will be the differentiator for this industry. And new technologies like inner anodes are yet to mature, and hopefully they get mature, and at an industrial level they are all implemented to see that our net carbon is getting real after implementation. And in India, we have around 4.1 million tons of primary aluminum smelting capacities, and all the various business houses are thinking of increasing these capacities. So the primary aluminum smelting, the process remains the same for more than a century. And the process was discovered by Mr. Hall and Herald, mostly at the same time. So the Hall Herald process is nothing but an electrolysis process by which alumina is getting dissolved in the cryolite and gets dissociated into aluminum and oxygen. And this oxygen gets combined with carbon to form carbon dioxide, and then aluminum, which is getting deposited at the bottom of the cathode, is being tapped out. And you can see that This is a schematic of individual parts where we have a cathode and we have an anode and we have the bath material, which is nothing but a cryolite, where the alumina gets dissolved and gets dissociated. The voltage record for this process is around 4 to 4.3 volts. And right now, people are also operating at a voltage of around 3.9 by doing a lot of changes in the conducting materials as well as also on the current densities. So in a pot line, we have around 350, 360 cells normally in a pot line in a EAP type of smelter. And the number of pot lines right now in the world has drastically increased. See, the technologies around the world are mostly from 3 or 4 technology suppliers. It was like Rio Tinto, Aluminium, and right now DX has been developed by EGA, and they are into very high amperage lines. And hydro aluminum has also its technology with low energy cells. And China has been also developing these technologies, and they have been leading this technology supply in the last 15 to 20 years. And Rusal is its own 550K Rusal technology. And then SAMI and GAMI are all most prominent technology suppliers in the region of China. So the amperage has ranging from 400 Ka to 600 Ka in high amperage lines. And there are lot more smelters which operates around 60 to 400 Ka in between. So what is the future for these low amperage pot lines? We will be discussing in the coming slides. And in the energy, if you see that there are pot lines which is operating around 12,500, and that has become a benchmark for the industry presently. So as we have discussed that there are pot lines which are operating from 65 Ka till 400 Ka. So what is the opportunity for these smelters which are running at low amperages? So we will be going through all the changes which can be done for increasing the amperage in these pot lines also in the coming slides. So in the amperage increase, why we wanted to do an amperage increase is like the production is directly proportional to the current which is flown in the pot lines. So for a 360 Ka pot lines with 360 pots and a current efficiency of around 94.5 in a pot line, the production per annum comes to around 360 KTPA. But if we have a 5% increase in the same pot line, we will be able to achieve around 378 KTPA. So that's an extra aluminum production of around 18 KTPA. So when coming to the cost of investment, while we are doing such type of amperage trips, you can see that the production increase has been plotted in the x-axis and the investment cost per ton is on the y-axis. For an ampere increase, it will be the lowest. It will come to around 500 to 600 dollars per ton, whereas for a greenfield, it will be around greater than $4,000 per ton minimum. So there's a big potential for any industry to go for an amperage increase. The other advantages are like there is no extra land which is required, and there are no additional infrastructure or very less infrastructure is required. And these amperage increases have been proven methods globally. And time might be little longer, but the investment cost is very, very less. So what happens when an amperage is increased in a pot line? So when an amperage is increased, the net heat, internal heat of the system increases. The internal heat is nothing but the increase in kilowatt hour with respect to the initial baseline energy. So it's nothing but the heat generated minus the heat absorbed. So that's the net heat in the system. So from the formula for calculating the heat in internal energy is like we have seen the voltage of the cell, we subtract the external as well as also the decomposition voltage and the auxiliary voltage that is multiplied by the current. While doing an amperage increase, we should see that the internal heat doesn't increase too much. So that will allow us to ramp up our amperage. And what are the other things which is happening during an amperage increase is like a lot of magnetic imbalances happen. And there is an increase in the metal velocity. And there are impacts on bus bars and insulations. There are also sometimes increase in emissions also, which has to be controlled through our gas treatment centers. And also we can see that people working at the shop floor are not having proper skills to handle such type of amperage increases. The typical energy losses in a spot line, in a pot, if we can see that major losses are through the yolks and through the anode cover of around 22%. And from in the long side, it is around 37 to 38%. And through the collector bars, it is 11.3%. So we know that the internal heat in the system has to be controlled to see that the amperages increases are done properly. Yeah. Coming to the levers available for increasing K in the pot lines. The first one is the operational discipline and the process optimization. We should be having a better operational discipline and the process control to see that the amperages increase or enabled. We also have a lining design changes. By doing a lining design change, we can increase the amperage by around 5 to 10% minimum. By installation of the magnetic compensation loop, we can reduce the vertical oscillations of the metal so that the ACD can be decreased, and by using this, we can increase the amperages as well. By implementation of forced cooling network across the cathodes, we can increase the heat losses so that amperage can also be increased. By increasing the anode size, we can see that amperages can be increased because the anode current density comes down, and this will enable us to increase the heat losses. And in some old smelters, we have part control systems which are not optimized, which are not having a narrow band of control. But in the latest part control systems, we have the option of controlling it in a very narrow range so that the energy excess heat input which is being given can also be eliminated. By installation of slotted anodes, we can reduce the bubble drop throughout the life cycle of the anode, and by reducing the bubble drop, we can also increase the amperages. And coming to the operational discipline, I mean that we should be able to do the work when it is required in a pot. We should not be having any pending works. All the scheduled works has to be done as per the plan. And the quality of work has to be excellent. If you can see in these images nearby, the first image shows a lot of skimming which is being accumulated in the pot. And the second one shows after the good shoveling how a pot looks like. And in the second case, if you can see a lot of flames coming out of the anode cover zone, and this is a bad work practice, and we can see a lot of airburn happening in such type of anodes, and that also contributes to the heat energy input into the system. The second one shows a good quality anode covering, which will help us to reduce the airburn and as well as also keep our energy constant. And we should be able to predict the abnormalities beforehand and not react to problems. We should always have a predictive capacity. And in a team, everybody understands the requirement and operating discipline. So people or the teams are sensitized before we go for any amperage increases. And there should be a synergy between all stakeholders like operation, maintenance, process, carbon, and cathodes. Here, any one of the department or one of the stakeholder fails to deliver, it has a cyclic impact on all the processing like. So these are all the few templates which is being normally used in a good quality, good pot line to see that all the parameters are all within the limits. And in the case of few abnormalities, if we can see that this is a block drop anode, and we can see spikes which is being done, and this is a part which has been not covered properly, and this is a part where there is no good anode covering. So focus on all these things and then make a good system to see that the operating discipline is perfect. By doing this, I think there is an opportunity always in the pot lines to increase the current by around 1 to 2%. The second one is the process optimization. The process optimization can be done in three options. So I will take it what are the three options. The first option, we increase the voltage while the current is being increased. In the sense that we are not reducing any ACD, we are just increasing the voltage as proportional to the current because of the ohmic drops. In this case, what happens? The total heat energy into the system is going to be high. And because of the high heat energy into the system, the side ledges will all melt and there is a potential of tap outs happening. But in many cases, we also find that the side ledges are operating at very, very thick levels. By increasing the current, sometimes some pot lines will be able to produce a better quality of ledge profile, and then that's an opportunity for increasing the current. But in some cases where there is a design which has been perfectly good, we will not be able to increase the amperages. And even in that cases, there is a risk of the metal tap out as shown in the figure. And in this case, since we are not reducing the voltages, we will be seeing that the energy per ton also increases in this case. Yeah, in the option 2 of process optimization, we see that the energy input is kept constant by decreasing the ACD. And the voltage is also decreased because of lower ACD. And this is the stable option most smelters have followed. In this case, we should do a still stability test in which the anodes are lowered and the noise is monitored. We lower the anodes till the extent the noise is becoming unstable. And that is the limit to which we can reduce the voltage. This is only an indicative practice which has to be followed while doing an amperage increase. But of course, we need to trade off the current efficiency loss against the amperage increase and then take a decision accordingly. And the third option is also a good option. Like we are increasing the heat input to the electrolyte, but at the same time, we lose the amount of heat outside the system. In this case, the specific energy consumption will increase, and we will also increase the heat losses through the anodes, through larger stubs, anode covers, etc. And we can also have an incremental metal pad to absorb the heat which has been input through higher voltage. For a successful process optimization plan, we should be having the following scheme to see that everything goes as per the plan. We should have an amperage increase target. Then we should have a simulation and modeling and find out an operating window while we are doing an amperage increase. And we should have an alignment with all the teams. Unless otherwise you align all with all the teams, then it's very impossible to do a big amperage increase. And we should have a religious checklist and audits of all the process parameters. And we should also focus on the cathode shell temperatures and the side ledges to avoid any risks of pot tap outs. You see, and then revisit the strategy continuously. Don't see that whenever there is a problem, we revert back and then come to normal. There will be issues, and then we should be able to revisit and then review and then make changes to our operating plans. Look for setbacks, and post that you learn and then implement stringent operating practices. And most important is train the peoples on new SOPs, and it has to be religiously executed. And coming to the lining design changes, there are improved lining design changes happened over the last 20 to 25 years, which comprises of changing into a totally graphitized blocks. So the graphitized block gives you an reduced cathode voltage drop, which can help you in increasing the current. And many smelters have already implemented the copper inset and the copper onset collector bar. This also reduces the CVD. And because of the CVD decrease, we should be able to increase the current. And there are smelters which have implemented the side insulation linings to see that more heat is getting out of the system, as we have discussed in the option 3. So these type of cathode design changes has already happened, and this will give you an uh, incremental potential to increase the current. And with these changes, we can expect something around 5 to 6% increase in the amperages with respect to the baseline. Coming to the magnetic compensation loop, what happens when we are doing an amperage increase? There is a lot of metal waves which is being formed, and the difference between the anode bottom and the metal level decreases. So in order to reduce the metal oscillations in a vertical field, we implement this magnetic compensation. So these are schematics of the magnetic compensation. Mostly there are bus bars which is being connected to the smaller rectifier, which supplies the current to flow in a direction opposite to the part line current, main part line current. So this creates a negative magnetic field and reduces the metal oscillations in the parts. The loops can be either internal loops or the external loops or the double loops, which can be both internal as well as also external. This can be done without disturbing the operations of the pot line, and can be done in a 2 to 3 years time frame. This will also help us in reducing the ACD of operation, and of course, by reducing the ACD, we mean that the voltages can also be reduced. And the forced cooling network. Forced cooling network is nothing but the a pipeline which is normally installed around the cathode at a level at metal to bath interface, and then the air is injected through a nozzle system, which allows the cathode shell to cool, and whatever the extra losses of heat are happening through this system, we will be able to increase the current in proportion to that. And this will also keep us the ledge profile in desired limits. And this has been helping the smelters to increase the pot line currents by around 3 to 4%. And many smelters have implemented this in the last 5 to 10 years. And we can also do an anode size increase by increasing the anode sizes. What we are meaning is, like, we should be able to keep the anode current density less. So when the anode current density is less, we can reduce the ACD itself, because the voltage drops are going to be less. But while we are doing an anode size increase, we should see that there is a ample capacity in the anode jacks to take the increased load. And we should have also see that the technological vehicles which supplies the anode from the carbon to the pot lines are all capable to handle such type of bigger anodes. And one more important thing to be seen in an anode increase program is that we should have a sufficient amount of center channel to see that alumina gets dissolved properly while the center channels are being reduced. If you have a very less amount of center channels, then it's very impossible for doing a anode area change and then get the benefits. So while we are doing an anode area change by increasing the length of the anode, in a green anode plant, we should be able to have some specific checklist which can cater to produce a larger anodes. We see that as the anodes requirements are going to be high because of the higher capacity, the green anode plant should have more capacity to produce. We need to also check on the size reduction capacities, whether the bud size reduction, as well as the core crushing capacities are all there to take the enhanced production. Check on the preheating capabilities and also on the sufficient mixing energy in the system, whether we can produce more anodes and larger anodes. Whether the paste cooler capacity also needs to be checked. And anyhow, since we are going to change the size of the anodes, the vibro compactor and the mold sites will also be changed. And also check on the cooling circuits for the anodes, as the temperatures might go out of the limits while we are producing the bigger anodes. And in a baking furnace, since we are producing a larger anodes, then there are a lot of checks which has to be done. First of all, we need to see that whether the pits are capable enough to handle this increase in size of the furnace, size of the anodes. If we see that in the diagram, in the first case, there is a capacity to load 3 anodes, but in the increased size of the anodes, we will not be able to load because the combustion zone is far down below. And in these cases, what we need to do is that increase the pit capacity, increase the height of the pit and the refractory walls to see that the combustion zone is also being targeting the increased length of the anodes. Also we need to check on the fume treatment capacities, because there will be increase in the gases which comes out of the system, and we should have sufficient capacity to handle such type of gases. And with an FTA, we should also check the packing and unpacking mechanisms and section mechanisms to see that there is no change in the there is no change to the normal operation practice. And in the rodding shop and anode handling areas, we should, first of all, we need to check the stub design, whether the stub hole and the stub diameter are capable enough to take an increased weight of the anode. Need to check the P&F conveying capacity. Check the furnace and cast iron pouring capacities as well. And since the buds which are going to come out of the pot room will have a higher size, and we need to check the bud processing equipments like primary crushers and the secondary crushers, whether it can be whether it is possible to accommodate bigger bud size anodes. And check the anode handling conveyors and cranes, and also check the anode pallet size, whether the pallet size is capable enough to take so much bigger anodes. The anode cleaning machines and stacking cranes has to be checked. And we also need to see that the storage capacities of the materials as well as the anodes are also sufficient enough to handle larger anodes. Because larger anodes means that larger space, we should have so much space as a buffer. And coming to the slotted anodes, presently, most of the smelters are having a slot being made in the green anodes. The green anodes, normally the slot height is less, because the reason is when you are going for a higher slot height, there is a chance of cracks formation in the green anodes. Right now, there are equipments which has been installed in many smelters to see that the slots are being cut in the baked anodes. The baked anode slot cutting also provides us an opportunity to increase the anode sizes also, because the slot width can also be less, and it can be done at a different profile, whether it can be from height to height, slanting slots, or the flat slots. And by the implementation of slotted anodes, we say that there is a bubble drop which always contributes to the increase in the voltage, and this bubble drop will come down. The reason behind is during the slots which are being made in the green anodes, the entire slot doesn't uh, stay for the entire life of the anodes. In this case, we need to see that the slots are there throughout the life cycle of the anodes. So we can also have an increased anode slots of around 400 mm, which normally is possible to cut in the baked anodes, and that will remain till the life of the anode cycle. And approximately 1.5 millivolts per centimeter of slot increase we will be able to get. And this is so much amount of energy which can be reduced through voltage drops can also be utilized for increasing the Ka. On the gas treatment center, while we are increasing the current, there is a gas temperature increase and there are also gas flow increases. And while these gas temperatures and gas flow increases, there will be a reduction in the absorption rate of HF and alumina. So what we need to do is that to reduce the temperature of the gases, we normally implement the heat exchangers in the heat exchangers which is being installed in the GTCs or in the duct lines to see that the temperature of which enters before the GTC has a lesser temperature when as compared to the baseline. Also, we can use the advanced packs which has a higher surface area and lower air to cloth ratio. You see in this graph, we can see there is the cloth qualities have changed very hugely, which can handle more increase in flow and requires reduction in the cleaning frequencies. And during amperage increases, we will always find that the quality of anode has a bigger impact. So in order to have a good quality of anodes, keep a check on all the following things. Like you see that the carbon dust in the cell should not get increased because it affects the bath resistance. When the bath resistance are affected, then there is a squeeze in the ACD. Well, there are a lot of spikes and there is an increase in the temperature, and that will bring down the phase of amperage increases. And increase in ER also will affect the amperage strip because there is an increase in the voltage, and if there is an increase in the voltage, then we will not be able to increase the amperage as required. And while doing an amperage increase, kindly check on the bus bars and the insulations. While an amperage is being increased, there is a lot of heat generation on the bus bars, and the bus bar temperatures should not go beyond the accepted values. So kindly do a regular check on the bus bar temperatures and also check the insulations of all the bus bars. There can be instances that the insulation of the bus bars are getting cracked, and that leads to a lot of catastrophe in the pot lines. So have a continuous check on all the insulations and the bus bar temperatures till the amperage creeps are successful and gives you a good results. And also check the pot room equipment's capability. First of all, do we have any sufficient pot tending equipments to handle increased pot operations? And whether we have sufficient technology vehicles like ALF3 charging vehicles, bath tapping vehicles, and bath pouring for startup, because in sometimes we require more bath to be poured in a new cathode design compared to the older cathode design cells. Normally, you should also have a bolted bridges to see that we are not getting affected because of any tap outs, and these bolted bridges can be more helpful in your risk elimination. And see that the anode transport vehicles also have the capacity to carry bigger anodes and bigger high weight anodes. And in cast houses, we will see that there is an increase in metal production. So we should be able to have increase in have the sufficient capacity to convert into the finished products. So do a study on that, and also do a capacity check on your technological vehicles, whether the vehicle can take you to the metal to the cast houses. Check on the tapping crucibles as well, whether the increase in metal production can be tapped with the existing crucibles. Either you increase the numbers or increasing the capacity of the ladles by reducing the lining. There are a lot of refractories which are come, which has the better properties than the original installations. So reduce the thickness of the lining so that we can increase the capacity of the ladles. And also see that skimming capacities at the cast houses areas are sufficient enough, and see that the crane capacities to handle more volume of metal at the cast houses are all there. So having gone through all the changes which has to be done in an amperage creep, just having an indicative timelines with all the levers, we can see that through process optimization, we can increase 1 to 5%, and the timelines will be around 3 to 6 months. Through a cathode lining change, it will take around 6 to 7 years of project time, because the pot lines, normally we cannot stop the pots in one instant, and it has to go through a scheduled phase out. But the capacities which we can be increased through cathode lining design will be around 1 to 10%. By anode dimension change, yes, there is a possibility of increase around 1 to 3%, and it can be done in 1 to 2 years time frame. And the magnetic compensation loop, we also can do it by around 1 to 2 years, and there is a possibility to increase 2 to 5% of current through magnetic compensation. And through forced cooling network, it takes little time, because it has to be done while the parts are going for repairs, or you can hibernate the parts and then do a welding or install the pipelines. That will also take around 2 to 3 years or 3 to 5 years of time, and this can give an opportunity to increase by around 2 to 3%. And normally, in most of the cases, all these things go in combination with one another. It's not that we can have a standalone, people don't do on a standalone basis, but it can be going through in a combination of one or two initiatives. But normally in an amperage tips, it's better to do a booster section implemented, which can have around 2 to 3% of the total parts, which has been taken for the booster section, where the amperage can be increased by Chetan margin, and do all the changes which you wanted to do, make it more optimized, use all the latest things in this booster section. Then you can implement in the overall pot line. This booster section will help you to do a trials, and so that while we are implementing in the total pot lines, it will be very easy for you to do the changes. Sometimes the business cycles also determine the phase of ramp ups. Means that whenever the LME is less, though sometimes it also happens that increasing the production doesn't give you any increase in any business benefit. So in that case, at that time, we should be doing slow amperage increases, or we should hold on the amperage increase. And also have a kind check on the raw material availabilities, whether you have sufficient raw materials like alumina, coke and pitch, and also ALF3, to see that whatever the increment in production, we will be able to have sufficient amount of raw materials and the energy as well. So coming to a conclusion, we can see that amperage increase is a lucrative option for realizing better business benefits. Mostly, at least around 50% of the smelters have already used this amperage increase programs to realize the benefits. And in any amperage increase program, it is very much important we take a structured approach, because whatever the learnings are all being implemented very structurally. Otherwise, if you go and do without any structured approach, there is a possibility of setbacks happening, and then might be we go into a wrong decisions that amperage increase doesn't give you any results. While we are also doing the focus on the reduction in energy consumption per ton, because right now in the market we know that energy has become a rare commodity and very high cost commodity as well. So, and in order to reduce the energy, see that you put the magnetic compensation loops and the cathode lining designs are designed properly to see that the energy consumption is less when compared to the baseline after an amperage increase program. And see that the energy mix is also being changed to have more cleaner energy in the system, so that whatever the commitment towards net zero is being also achieved. And that's my last slide. And of course, thank you so much, the IBAAS team and all the people who are listening for this presentation to give their precious time. Thank you.
Thanks, Sasikumar, for excellent presentation. Now this is open for discussion. So please ask questions to Mr. Sasikumar. He is there online. Yeah, please. Sudhir Patel, please ask your question. Yeah, good. Sasikumar, it was good presentation. Excellent work.
Yeah, thank you, Ashok. Thank you.
Yeah. So let us start our question answer session, and it's open for questions. I can see Mark Dupis also, a authority on aluminium smelter. Mark, where are you?
I'm here. It's a
Mark.
very good presentation. You hit all the long list, but it's all important, especially anode quality, I would say, and having the requirement for a booster section, so you can optimize the control before implementing for full pot line. May I ask, who is giving you support for installing booster section or lining design suggestion? Are you doing all yourself?
Yeah, Mark, good afternoon. We have started the engineering of the booster section. Yeah, some places we are taking the outside glucose support as well. And we are doing the design side. We are also doing internally, and then after that we get an approval from Binco.
Binco is helping you.
Yeah.
Okay.
Mark, yeah, any more question? Winco is
No,
also, yeah. Yeah, Sanjay, please ask question.
Sir, I have asked, good afternoon, sir. I have asked that would it be any role of anode coating if you anode and cathode coating is done nowadays? So if you had done any anode or cathode coating like that, is in your amperage grip on this, what the amperage matching you say, does it play any role on that?
Yeah, thank you for that question, Sanjay. See, the anode coating, it will help out in increasing the anode life cycle. Okay, so if we have around 76 shifts of anode life cycle, if you have an anode coating, we can increase the life cycle to 80 shifts. But what we are in this case for an amperage increase, which is required, is more an anode area increase, so that the anode current density comes down. Yes, it will help out in increasing the anode life cycle, but for a higher amperage increase, it's better to increase the anode area to see that density comes down.
So I got your point. Like it is the added benefit. Like this is one, and this is another bonus.
Yeah, absolutely.
Thank you very much, sir.
Yeah, Satyanarayan Das, please, Mr. Das.
Yeah. I have two questions. In our hotline 180K, we have seen that without anode quality improvement, particularly carboxy reactivity residue, thermal conductivity, and these things, you cannot increase the current. It leads to dusting in the pot and a vicious circle and a drastic reduction in current efficiency. How do you handle such situation? What is the, how much and what kind of anode is critical? Which quality is in anode is very important when you go for higher K?
See, as such, as Mark was saying before, that the anode quality as a whole is a main important parameter before you go on for any amperage increase. Okay, so
Yeah.
for me, if you consider that the ER is also a major important factor before we do an amperage increase, because it directly affects the voltage, and whenever the voltage is high, we cannot increase the current as well. So that's one thing. And see that the carbon dust formation, so carbon reasons for carbon dust formation has to be less. It can come either from the pot as well as also because of your ERR increase, because ERR sometimes goes down, and that could also one of the reasons we can see a lot of dusting. To see that the before an amperage tape, we should have a stable process, and after that only we should be able to increase the amperages. So before having any problems, if you have any problems in the anode in the particular normal routine itself, then I think it's better to stabilize it, make it normal, and then only plan for an amperage increase.
No, what is the range of CRR or
See, CRR,
critical?
CRR in the most stable plant, it should be around 90 plus. Okay, so on ERR, we are at around 70, 74, 72, 73, and ER less than 57. So these are all the parameters which we should target before going for any.
That means if you are around 80, 84 ARR, CRR, you cannot go for a amperage increase of 3 to 4K like that.
Yeah, I can better you focus on increasing the CRR, then you should think of increasing the amperage.
So just you have distributed the contribution of force convection network so much, anode increase so much. How much you attribute to anode quality improvement for amperage? What percentage?
See, that depends on the base quality of the anode. Okay, so if you say that the base quality of the anode is 84% ARR and CRR and ARR of around 65% and ER of around 57, I think might be there is a possibility to go for a 2% increase also. Okay. So we need to see that what is the baseline quality presently which is there. If there is, for example, you are right now itself operating at around 92%, everything is good. So I think in that case might be around 1% is the maximum which you can achieve because of the anode quality increase.
Lastly, this we have seen that the carbon plant is the major bottleneck for a amperage creep. So mostly it is in back oven. How do you accommodate such larger anode? Because it is already designed for there is little cushion for accommodating larger anode. So how could you adjust to such a situation?
See, if the pits which you have designed doesn't have the capability to handle the increased length of the anode. So we need to see that the pit height has to be increased. So there are a lot of OEMs and design agencies which we do the modeling and also give you the engineering for increasing the pit height as well as also on the FTC capacities. So in that case, we need to see that we should do the pit height increase, then do an engineering, then only revert increase. Because with a larger anodes, if we don't have a pit depth, then it's not possible for increasing the current. Sorry, increasing the size of the anode.
So that means this will take at least 1 to 2 years if you re-engineer the pit
Yes.
increase height.
Yeah, increase pit height, it will take time. So there are different concepts which is being made. Sometimes plants used to demolish the total lining and then build it. Till that time, they outsource the carbon blocks from outside. That is one. Or you do it in section-wise basis and then partially convert it. So it's like we need to see where the trade-off and the economic balance comes up.
As a GTC, have you installed a heat exchanger, as you say? Have you
See, now
installed?
presently it is not required for us, but for during summer season, there is a temperature increase. Yes, if you go for a 400 KSLs, then we might need to reduce the temperature. So we are looking for different options, either to have a heat exchanger or through installation of fins, we can reduce the temperature, gas temperature as well. So we're just not finalized on that. Once we are doing this booster section, we should be able to have some results. Based on that, we will take action.
Now you are managing without all this in your 370 or what you are achieving, isn't it?
Yeah, right now we have not installed any heat exchangers or any additional cooling mechanism. So we have increased the KA by around 15 KA from the original design, 360. So till now it is not required. Yes, during my summer days, we wanted to have all our air dilution dampers open for 100%. And that's how we are managing right now.
Okay, thanks a lot. Yeah,
Mr. Khalil,
good
any
presentation.
question? Yeah, Khalil, any question?
Khalil sir, good afternoon.
Yeah.
Shashi, good afternoon.
Yeah, good afternoon, Vivek.
Very nice presentation.
Yeah,
You covered all the things. Covered all the things.
So it was a checklist type of thing which we made. Anyhow, if it was a single one, then we need to go very deep into the system. So I just wanted to have a type of checklist when we think of an amperage pit.
Did you implement the booster, the compensation loop, or you're not? It's not required.
No, we will have a compensation loop as well, Mark.
Soon, okay. Because what I know about you're not there yet, but if you approach 400 KA, you will need a compensation.
Yes.
Yeah,
that's what we are planning. So in a booster section, we are planning for booster as well as the compensation. So once this is done, we will also have the magnetic compensation for the whole line.
Okay. Who is doing the engineering for this installation of booster?
We have done in-house.
You're doing in-house. Oh, okay.
And just adding to what Shashi has said to Mr. Das, more than having the values, good values of CRR, it is important that the standard deviation of the anode should be less. So that will also help you a lot. If you are able to reduce it, the standard deviation, that means difference between different anodes, then it will certainly help you to the greater extent at the outset.
Yeah, thank you, Vivek, for adding that point. That's also very important. Yeah.
Yes. Very good point. Yes. Yeah, Mr. Khalil Khaji, any questions?
Khalil Khaji, sir will give some solutions. She will not ask questions.
We need to ask him the questions. But we are not able to see him.
No, Khalilji is visible.
Visible?
Yes. Please see him. Yeah, Yeah, he is there in the
Okay.
picture. Okay. And any question, Mr. Sudhir Patel? And okay. Shankar, please ask any question. Shankar.
Hi, Sashi. Good
Hi, sir.
presentation. Yeah,
Thank
I
you.
have just one query. Currently, which plant has the lowest energy consumption? Like you said, 12,500 they have achieved. Which plant? Any idea?
The Chinese, they are climbing, I think one of the plant in one China, they are climbing at around 12,500 something. So that's
Okay.
what the numbers we get.
This is AC or DC?
This is DC.
DC. Okay.
Yeah.
Good. Thanks.
I think Alouette number will also be less. They are also operating at low values.
Okay.
Any more?
Semi is doing a design with what they call NCCT plus. It is big collector bar with copper insert, and they're getting quite low in energy consumption.
Okay.
Yes.
But they are not trying to create the amperage at the same time. They are only decreasing the energy. So it's very difficult to do both. You either you creep, so you produce more, or you decrease the energy
Yes.
consumption. But you cannot do both. There's no miracle.
Yeah. Okay.
Okay. There is a question from Mr. Sudhir Patel. How you are going to handle increased metal production with same PTA crane?
See, there are two ways. One is the easy option is to put one more PTMs. Okay, so that's one thing we can handle. Second thing is that we are also working on the reliability or the availability part of the existing PTMs itself. So the existing PTMs availability might we are focusing on reliability as well to see that how we can increase the availability of this PTM. So that's where, and of course we have also asked for the OEM to see that when we are increasing the size of the anodes, the total weight is also going to increase, whether the extraction system is capable enough to lift the anodes after the breaking. So these are all the two or three things which we should see while checking this. And of course, the insulation part also, when we are increasing the amperages also, we are also given an inquiry to see that all the systems are going to be within the limits. So these are all the three things which we need to see.
Okay.
Yeah.
Okay. So any more questions from anybody? There are about 50-60 persons are here. So any more question, or we will upload this thing on IBAAS website. And if you have any question, please direct it to Sasikumar or to IBAAS office. We will get the answer for you. And last but not the least, it is the conference which we are organizing during 25th to 27th. Vivek Saxena is laughing. So, so we invite all of you to participate. So there will be a big team from Hindalco. We are expecting a team from Vedanta and Valco. So Vivek Saxena ji, see if you can participate in this conference. We'll welcome you all.
Yeah, Ashok ji, we have a lot of people presenting papers in that IBAAS, so there will be a big team coming from Hindalco.
Yeah. There are 100 people are there almost from Hindalco, and our 30 persons are there from Vedanta and Valco. So we'll welcome all of you, and it will be a great get together in Goa. Thank you very much for all your attention. And Vivek ji, if you want to have a next lecture series, October, we can have you in the one of your presentation.
Yeah, thank you.
Okay, so we will approach you during October after this conference. September, there will be no lecture, but October, again, we will resume. Okay?
Thank you.
Sure. Thank you.
Thank you.
Thank you.
Everybody. Yeah. Thanks, everybody.
Okay, bye. Thank you. Bye.
Thank you, Mar. Thank you.
Thank you. Bye.
Bye. Thank you.